Hello my dear students, welcome to the session. Till last session we have discussed very important problems on initial conditions, how to determine the initial conditions. So I think by this time you have become master in finding the initial conditions. Okay, I explained you a step-by-step procedure. Don't forget that step-by-step procedure. Okay, you never do any mistake if you follow my step-by-step procedure, whatever I explained. Okay, now the next part of it is like we need to find the time response. See, I told you once again, just let me recollect the objective of the transient analysis. What is the object of transient analysis? The objective is, okay, to understand the dynamics, right? Okay, we want to understand the dynamics. The objective of transient analysis is what? To understand the dynamics. This is our objective, understand the dynamics of the system. Dynamics of the system. So how the system is behaving after the system subjected to any disturbance. But to understand the dynamics, you require a time response. Yes or no, all of you? You require a time response, x of t. X might be current, voltage, or anything it might be. For that, you require a differential equation. Yes or no, all of you? Now, when you solve this differential equation, okay, if you want to solve the differential equation, you require initial conditions. Yes or no, all of you? Okay, to find the x of t, you require a differential equation. Okay, and for that you require initial conditions. This is the complete procedure of how you evaluate the dynamics of a particular system. But there are many methods actually involved in this. I mean, there is one more method also involved in this, not only from the differential equations, because certain problems to find this x of t. What is x of t actually here? Time response. Yes or no? This is nothing but what? Time response. See, the time response can be determined not only using differential equations, but also the Laplace transforms. Okay, so there are two methods involved in this. One is a differential equation approach, the other is Laplace transformation approach. Understand all of you? Okay, Laplace transformation and differential equation, both the methods can be applied. So what we do is, first we discuss the application of differential equations to the electric circuits to find the time response. Then later we will see the Laplace transformations applications. There are certain problems which cannot be solved using the differential equations to find the time response. There are some problems, okay? Because particularly in case of impulse response, particularly in case of step shifting functions or any shifting functions, exponential input, okay, or sinusoidal input, something like that, okay? But here, particularly, I'm talking about particularly exponential, or else let us say the shifting functions or impulse response. In that cases, definitely the differential equations approach will be very, very difficult. In such cases, those limitations can be overcome by Laplace transformation. Okay, I can tell you in the differential equations, impulse input is given to the system, and shifting functions like u of t minus a, something like that. When these kinds of inputs are given, okay, inputs are given, the solution using the differential equations will become very, very difficult, okay, or almost impossible. In such cases, the solutions can be obtained, or the time response can be obtained using the Laplace transformation approach easily. Okay, so I'm going to explain you first how we apply the differential equations. In that differential equations approach also, first I explain you the conventional method, okay, the usual procedure. Then I'll give you a simple shortcut technique to find the time response using the differential equations approach. Understand all of you? Because time is very important for us in the competitive exams. I will explain you both the methods. We'll go conceptual first. We'll try to learn how we apply the differential equations to the given circuits to find the time response. And also we'll learn the shortcut techniques. Later we will switch over toward the Laplace transformations, because there are certain difficulties we are facing using the differential equations. Where are we facing? Tell me all of you. When the circuit is consisting of impulse input, that means impulse response you're going to get. When the circuit is excited by the step function or any other function using shifting functions. Understand all of you, when there is a shifting function, okay, input, then definitely the time response finding using the differential equations approach is going to be very, very difficult, or sometimes it is impossible also. That is why I'll explain you that better. Okay. So just note down once again here, objective of the transient analysis is to understand the dynamics of the system. For that you require a time response. If you want to find a time response, you have differential equations and Laplace transforms. Application of differential equations and application of application of Laplace transformations. But what is the drawback of this particular method? Shifting functions and impulse inputs are present. The differential equations method is very, very difficult. This drawback of this method can be overcome using what? Laplace transformations. Okay, I hope you understand this. Now let us take a generalized differential equation, and we'll discuss just some fundamentals of differential equations solution. You already know in mathematics, but still I would like to just give a quick recap of the differential equations. Okay, so now put the heading application of differential equations. Let the differential equation of a given circuit be d power n I of t by dt power n plus, okay, this is A1, A2, A0, okay, A0 and A1 d power n minus 1 I of t by dt power n minus 1 plus and so on a n minus 1 d I of t by dt plus a n I of t is equal to v of t. See, the entire differential equation is in terms of current. Usually it happens only when you apply Kirchhoff's voltage law or mesh analysis. In mesh analysis, what is a variable? Current is a variable. Okay. So assume that there is a voltage excitation here. Say this is equation 1. This equation 1 is obtained using mesh analysis, okay, or Kirchhoff's voltage law. Okay, obviously mesh analysis deals with Kirchhoff's voltage law. This is the first equation. Secondly, you can also obtain the differential equation using what? Node analysis or KCL. So I can say B naught d power n v of t by dt power n plus A1 d power n minus 1 v of t by dt power n minus 1 plus and so on. B minus, this is not A1, this is B1, okay, B1 Bn minus 1 dv of t by dt plus Bn v of t is equal to I of t. Say it is equation 2. Now node analysis KCL. Understand all of you? Okay. Now solving the equations. Okay, I can express first. Let us consider equation 1. From equation 1, okay, let me take. Can I write something like this? F of d, a differential polynomial, okay, into I of t can be written as what? V of t. Now you have the solution. Solution will give you I of t is equal to complementary function plus particular integral. You understand all of it? Okay? Some complementary function, some particular integral part is there. Complementary function is also known as homogeneous solution. Particular integral is also known as particular solution. Complementary function is known as what? Homogeneous solution. particular integral is nothing but particular solution. Okay, we have different names in the mathematics. Okay, you can use the different names. In place of complementary function, you can also call it homogeneous solution. Okay, now look at this, all of you. Look at this, all of you. Okay, I think I will give you some time to note down that part. First, look at this here. Now, you know that we have solved a differential equation, right? What is the differential equation we have solved? I think you remember, all of you. Okay, d square plus 3d plus 2 of, okay, I of t is equal to 10. And finally, you got the solution I of t will be k1 e power minus t plus k2 e power minus 2t plus 5. This is what the solution you got using complementary function plus particular integral. Combination of these two. This is what you got, complementary function. This is a particular integral you got. The same example I have taken when I explained you the basic concepts of, okay, the introduction part of the transient analysis. Understand, all of you? Okay. But if you observe carefully here, now this particular part is changing with respect to time. Yes or no, all of you? This part is changing with respect to time or not? Yes, it is changing. Okay. But this is not changing with respect to time. That means as the response changes with respect to time, or any response that changes with respect to time, you generally call it as what? Transient response. The response which does not change with respect to time, constant, continuously it is giving constant output, then that response is called what? Steady state response. Therefore, now in our electrical engineering terminology or in our transient analysis terminology, okay, let us not use the complementary function. That is, mathematically we use it, but in our class, let us try to use it is a transient response. Understand, all of you? Okay. Now this is a steady state response. I hope you understand this. Transient response, steady state response. You have even some more names for it. Just very interesting. Just look at this, all of you. See, this particular part is a transient response which changes with respect to time. But as the time increases, this particular part will be decaying or not. This entire part is dying out or not, because it is minus e power minus t, e power minus 2t. As the time t tends to infinity, these values are decaying exponentially, and finally they become 0 as t becomes infinity. Yes or no, all of you? Okay. That means what? This entire component is not existing continuously for a long time, only for a short time. That means only temporarily it is existing, and whereas this particular part is existing permanently because it is not a function of time. Yes or no, all of you? Okay. Therefore, that is why the transient response is also called temporary response. Temporary response. This is called permanent response. Permanent response. Understand, all of you? Okay. Temporary response and permanent response. Now, some more names are there. Just look at this. Very interesting, because in the exam, when problem is designed, he might be using transient response or temporary response. But you must understand that transient response, temporary response, both are same. Okay. Now, one more important thing here. This particular response, okay, this particular response is appearing even if input is not given. Understand, all of you? Okay. Without input also, you are able to get that response. Okay. But this response is obtained because of what? The input given to the system. Yes or no, all of you? Okay. That means without input also, you are getting that response. For example, I'll tell you here something like this. You turned off the fan. The fan is actually rotating with 1000 RPM speed. Okay. Some input is given to the fan, and the fan is rotating with a speed, let us say 1000 RPM continuously. That means it is in steady state. Now you turn off the fan. What will happen? The 1000 RPM speed will come to what? 0 speed. But it does not come to that 0 speed instantaneously. Okay. The response is changing from 1000 RPM to 0 RPM. Okay. Slowly, with respect to time, that response is changing. Yes or no, all of you? Okay. With respect to time, the response is changing, and finally it is coming down to what? 0 RPM. Understand, all of you? Okay. But you're also getting the response even after you turned off the fan. Though there is no input to the system, but still that response is existing for some time. Yes or no, all of you? But how that response is coming? Without even input also. It is coming naturally. Yes or no, all of you? Okay? Naturally, without any source, source free. You call it source free response or you call it natural response. Okay? So this temporary response or transient response are also called source free response, or you call it natural response. Natural response. But this response will come only when there is a force. Understand all of you? Okay? When there is a force, okay, then only it will appear. You have a fan now with a 0 RPM speed. Now you suddenly turn on. What will happen? It will slowly pick up. Now the response is changing with respect to time. Now this is the transient, right? Now again, finally it is reaching to what 1000 RPM. That means the transients are died out. Now it is rotating constantly with 1000 RPM. That's all of you, okay? Now 1000 RPM you have achieved. It is all because you have given input to the fan. That means when there is an input, when there is a source, when there is a force, then only you got that response. The 1000 RPM is what steady state value. Yes or no, all of you? Okay. Now the fan is rotating continuously with 1000 RPM. That means it has reached the steady state. Initially it was in steady state 0. You turned on. It entered into transient state where that response is changing with respect to time. And finally it reached 1000 RPM. That is another equilibrium state or steady state. Yes or no, all of you? Okay. So that steady state is appeared. It's all because of the given force. That is nothing but you have given some input. Therefore, this response is called forced response. What is it called? Forced response. I hope you understand the point. So very, very important. And one more important point you can observe. Directly, indirectly, how many forces are acting on the system now? See, you actually explained why the transients are observed. Very beginning class I explained you why the transients are observed. The transients are observed because of the initial amount of energy stored in the inductor and capacitors. They are the storage devices. Wherever you have storage devices, there definitely you will get the transients. Yes or no, all of you? So who is the main cause for this particular response? Who is the main cause? Initial amount of energy stored. That means initial states. Yes or no, all of you? Initial states are the main cause, okay, for this particular transient response. But who is the main cause for this particular forced response? The external input. If there is no external input given to the system, then you can't get that steady state response. Yes or no, all of you? Okay. So directly or indirectly, now there are two inputs are acting. One is the actual input given to the system. Now the other is the internal states are acting like inputs in the system. And because of the internal states or initial energy, both are same, okay, internal states, you are getting a response. That response is the transient response. And because of the external input, you are getting a response. That response is called steady state response. Yes or no, all of you? Okay. Now, when you have multiple inputs in the system, immediately you recollect one theorem. What is that theorem? Tell me, all of you. What is that theorem? Superposition theorem. According to superposition theorem, the response due to the first input, okay, is calculated when the second input is suppressed. Now the response due to the second input can be calculated when the first input is suppressed. Yes or no, all of you? Okay. Now using the concept, now you can say here, now I get this particular response when according to superposition theorem, okay, there are two inputs. One is the internal states, okay, or initial states. Initial states or internal states, okay, or initial states otherwise. Initial states is a one input, and the actual input given to the system, input to the system is another input. Now I would like to find the response due to the initial states. What shall I do now? I have to suppress this input. I have to make this input 0. Yes or no, all of you? If I want to find the response due to the input, I have to make this initial states to 0. Yes or no, all of you? Okay. Therefore, the response that you obtained here because of the initial states, it can be determined only when the actual input given to the system is made 0. That means you are making that input 0 and finding the response. That is why you call it zero input response. It's a very, very interesting point. Understand all of you, okay? Sometimes in the exam, the zero input response is given as below. That means he has given indirectly what? Transient response only. Okay? Now here it is given as what? Now zero state response, because you can calculate this response by suppressing the initial states according to the superposition theorem. So zero state response. Zero state response, zero input response. There are different names for complementary function, homogeneous according to mathematician, particular integral, particular solution according to mathematician. But according to our electrical engineer, you are supposed to call the terms as what? Transient response, temporary response, source free or natural response, zero input response. Coming to this now, steady state response, permanent response, forced response, zero state response. Okay, so please note down. I'll give some time. All of you please note down quickly here this particular part. It's very, very important. See, the numericals are very simple to solve, but one should understand the concept behind why we are studying this particular part and what are the important points to be observed. Okay, this is an example I have taken to make you understand. Clearly note down. Any differential equation can be expressed like this. F of d is a differential polynomial. I of t and v of t. The solution of that I of t can be expressed as complementary function plus particular integral. Now we have different names for complementary function as well as particular integral. Let us use the term now onwards transient response and steady state response. Understand all of it? Okay? Now let us see the step-by-step approach. Steps important. Steps to determine time response by by application of differential equations. By application of differential equations. Okay, so I told you already that I am going to discuss first normal method, I mean conventional method or a traditional method. Then I will explain you in the exam point of view how we have to solve the problems, how we can find the time response using simple formulas and simple techniques. Okay, but let us learn first of all how we apply. Now, step-by-step approach, right? Step 1, first step. What is the first step? To find the time response, first of all, you must have a differential equation. Obtain differential equation for t greater than 0 using KVL or KCL or both. Okay, what is the differential equation? Usually it is in that form only, right? And solve it. Once you solve it, what will you get, Nana? I of t, for example, you are working on current, let us say. Current I of t will become what? ITR. I hope you understand now. No complementary function, particular integral terminology now. Now onwards, transient and steady state. ITR plus ISS. ITR plus ISS. Step 2. Step 2. See, when you solve this particular equation, the differential equation, you get the solution like this. But ITR consists of what? Arbitrary constants. Those arbitrary constants can be determined only using what? Initial conditions. That is why we determine Okay, determine t equal to 0 plus conditions. That means initial conditions. Okay, initial conditions. Initial conditions, there is a procedure. What is that? Three-step approach again. Whatever we learnt in the earlier sessions on initial conditions, how to determine. Okay, you just take the entire calculation part and apply here. Just copy and paste here. That is t equal to 0 minus first we do, then t equal to 0 plus we go. Okay, and most probably you will get the problems on what the first order derivative terms only. That too, I will be current through the inductor, V will be voltage across the capacitor, usually 99.99%. But even if you do not get current through inductor, voltage across capacitor based problems, I told you already, C, nothing but what you have to obtain the differential equation for t greater than 0, and from that you have to proceed. Anyway, the differential equation is already obtained here. Yes, and all of you, the same thing you can use and go for higher order derivative terms. Now, step 3. Once you find the initial conditions, now you apply initial conditions to equation 1. Apply t equal to 0 plus conditions to equation 1 and determine. Okay? And determine the arbitrary constants. And hence find the solution of I of t. That's it. The solution of I of t. So this is a systematic approach and procedure to determine the time response by applying or by application of differential equations approach. The conventional method I will explain you first, and then I will move on to the simple technique how we can apply. Okay, so please note down that quickly. Meanwhile, I just note down one problem here. Question number 1. Question number 1. Question number 1. I think all of you noted down this. Question number 1. Okay. So what is the question number 1 in the classroom workbook? You please go through that question. The given circuit is in steady state for a long time with the switch K kept open. At t equal to 0, the switch is closed. Determine I of t for t greater than or equal to 0. Determine I of t for t greater than or equal to 0. This is the question given. Okay. So let us follow step-by-step procedure to avoid all the confusions and all. Okay. So let me just take it off. Step 1. What is the step 1? Obtain a differential equation. Yes or no? For t greater than 0 using either KCL or KVL. Yes or no? So let's do that. Using either KCL or KVL, let us find the differential equation. Step 1. For t greater than 0, differential equation can be obtained, because you require current as a variable, definitely KVL is the only option you have. So I of t into R plus L d I of t by dt, yes or no, is equal to, can I take V? Yes, I can take V. Can I find this one as d by dt is nothing but capital D? Yes or no, all of you? So d plus R by L, R by L, the L can be taken here, L can be taken to this side, and into I of t can be taken as what? Capital V. From this, you can find the complementary function, but we are calling it as a transient response. ITR is nothing but what? ITR is nothing but what actually? The roots when you find, D is equal to minus R by L. Therefore, ITR is nothing but K into e power minus R by LT. There is only one arbitrary constant because the order of the differential equation is 1. For nth order differential equation, you will get n number of arbitrary constants. Okay. Next, ISS, steady state, nothing but particular integral, but we call it steady state. So ISS can be determined as 1 by f of d, that is d plus R by L, into V by L. This is V by L, yes or no? V by L. Into e power 0t. When you substitute 0 here, V by L by R by L, and finally you get 1 by 0 plus R by L into V by L. Finally you got V by R. Okay, so this is what ISS. ISS is nothing but V by RL. V by R. Okay. Now adding these two will give you a complete solution. I of t. Therefore, I of t, K into e power minus R by LT plus V by R. This is what the complete solution, but it is still incomplete because of K. So let us call it equation 1. In step 1, I have indicated clearly equation 1. You call this one as an equation 1. Okay. Now to find this arbitrary constant, we must deal with what? Initial conditions. Step 1. What is step 1 actually here? Initial conditions. When we deal with t equal to 0 plus conditions are to be determined, but for that step A, we need to go for t equal to 0 minus. What is I actually here? I is current through inductor. Yes or no, all of you? Current through inductor at t equal to 0 plus can be determined easily from first step itself. There is no need to go for second step. But for that you require I of 0 minus. Switch open, therefore 0. Therefore I of 0 plus is nothing but what? I of 0 minus, nothing but 0. So there is no need to go for step B, step C, and so on and so forth. Now let's go for step 3. Now apply t equal to 0 plus conditions to equation 1. So what will you get? I of 0 plus is equal to, okay, K into 1 plus V by R. What is this I of 0 plus, Nana? Already you got 0. This value you know very well. Therefore, K is equal to minus V by R. Understand? Therefore, now the complete solution will become minus V by R into e power minus R by L into T plus V by R. This is the complete response. Understand all of you? Okay, this is the complete response. But we can even write this in a simple way, that I of t can be written as V by R is taken common 1 minus e power minus t by tau. Okay, it's very, very important, where tau is equal to, okay, L by R. Understand all of you? Okay, where tau is equal to what? L by R. Tau is called time constant. Time constant, which always refers to speed of the response. Speed of the response. Speed of the response. If tau is larger, then you call it a sluggish response or slow response. Slow response or sluggish response. If tau is smaller, then you call it a faster response. Understand all of you, okay? This is the significance of tau. So always you must maintain the tau as smaller as possible so that the response is faster to reach the steady state. Okay? So if you draw that waveform, it looks like this. This is t, and now at t equal to 0, what is I of 0? Is 0. At t equal to infinity, what is I of infinity? V by R. Yes or no, all of you? If you substitute here, this transients will die out as the t tends to infinity. Finally, you are left with what? V by R. Okay. Therefore, this is a steady state value, V by R. And finally, it starts at 0 and it reaches exponentially, okay, it reaches V by R. Now, at t equal to tau, I of tau will be e power minus t by tau. Understand all of you, okay? E power minus t by tau. That means t is nothing but tau e power minus 1. 1 minus e power minus 1. Finally, you got 1 minus e power minus 1 is nothing but what? 0.632 V by R. Okay? You know that V by R is nothing but it's a final value. And the time taken for the response to reach 63.2% of its final value can be called as what? Time constant. Time constant is also seconds. It is also a time. But what is that time? How you define it? It is defined as it is the time taken for the response to reach 63.2% of its final value, because it is 0.632 times of V by R. So I can say this is 50%. This is somewhere, let us say 63.2%. Okay. This is V by R. Now 0.632 times of V by R. Okay. As a time tends to tau, the response reaches 0.632. So therefore, the time constant can be defined as, here in this particular case, it is a time taken for the response to reach 63.2% of its final value. Understand all of you, okay? So please note down. This is a first order circuit. It's very clear. RL circuit is always a first order circuit. It is a first order circuit because the differential equation, you can see, it is a first order differential equation. For the first order circuit, okay, you got the response that I of t is equal to V by R into 1 minus e power minus t by tau. It's an exponentially increasing function. Okay, so please note down this. This is a normal or conventional or else a traditional method to determine the time response using application. Hope I think you completed this part. Okay, you continue with that. Meanwhile, I just take another problem. We'll next go with the RC series circuit. So first we realize how we apply the differential equations method to find the time response, because this calculation part is very, very important. We're going to discuss the transients in AC circuits, particularly when the circuit is excited by the sinusoidal input. So how we actually solve the problem, we are going to see that. In that case, this experience will help you a lot. Understand all of you, okay? Hope I think this part is also over. Now let's go with the RC series circuit. RC series circuit. Again, the same step by step. For t greater than 0, first you obtain the differential equation. IR plus 1 by c integral I dt is equal to v. Differentiating, okay, differentiating with respect to time, then you get di by dt into r plus I by c is equal to, because it is constant DC source, you would get 0. Finally, you get d plus 1 by rc into I of t is equal to 0. Then I transients will become, because you know that d is equal to minus 1 by rc, you can write yes or no. What is the root of this differential polynomial? Minus 1 by rc. Therefore, k into e power minus 1 by rc into t. I steady state will become 0. What is the reason? This differential equation, you see the right side quantity here, 0. Therefore, the particular integral or else steady state value is also 0. Now, if you see, the total response is nothing but what? K times e power minus 1 by rc into t. Call this is the first equation. And now you require initial conditions. Step 2. T equal to 0 plus conditions. For that, you have a step-by-step approach. For that, you need t equal to 0 minus. What is VC of 0 minus? Definitely 0. Yes or no? We determine all these things. I don't want to spend much time on this. Okay. Now, t equal to 0 plus conditions. It is closed, acting like a short circuit because voltage 0. Finally, you got I of 0 plus is nothing but V by R. Now, step 3. Step 3. Apply t equal to 0 plus conditions to equation 1. If you apply I of 0 plus is equal to k into 1. Okay, but what is this value? V by R. Therefore, k is equal to V by R. And now you find the total response. I of t will be V by R into e power minus t by tau. Okay, where tau is equal to RC. The time constant again. Understand all of you? Okay. So now let me draw the circuit. Waveform clearly. Now the waveform can be drawn clearly. When I of 0 is taken, what is that value? V by R. When I of infinity is taken, it is 0. When I of t is taken, okay, what do you get here? E power minus 1. E power minus 1, if you just apply, what will you get here, Nana? Just find that 1 minus 0.632. 1 minus 0.632 is nothing but 0.368. Okay, e power minus 1 is nothing but what? 0.368. Okay, so this is actually you get V by R 0.368 times of, okay, V by R. So it's very clear. From this, it's very clear that exponentially decaying function. This is V by R. This is I of t. This is time t. And this is V by R e power minus t by tau. 0.368, whatever you got the value here, 0.368, this is 50%, and 0.368 somewhere, if you can say, 0.368 V by R. That's it. 36.8% of initial value. It's a time taken for the response. It is a time taken for the response. It's a time taken for the response to reach 36.8% of its initial value. Its initial value. That's it. You understand all of you? Okay. So this is how you need to define it, and please note down. I stop the session here and we'll discuss the remaining